How Newton could unravel gravity was adequate to permit us to fly from the Earth to the Moon. At any rate, it sort of got to make you laugh to imagine that you would have the choice to go the entire way to the Moon and back. If that's finally useful, it's something I gather. All that in our universe seems, apparently, to be splendid. There are rules governing the whole universe. However, specific secrets have remained peculiar despite various significant stretches of evaluation. For example, why does time travel in one direction? What is the possibility of reality? Why does gravity exist? Why does time dial down when we travel at the speed of light? These are questions that have captivated us for a seriously long time. Think about how possible it is that I let you understand that gravity is clearly deceptive. It's basically a form of the human brain. This could give off an impression of being wavering, but that's conclusively the very thing that the popular physicist Brian Cox has as of late claimed. Could we dive into the possibility of gravity and why time does bend? To sort out what in the world is the matter with gravity, we, in fact, need to go beyond Newton. The issue lies not so much in what he got right, but in what he neglected to resolve. There's an issue with Newton's theory of gravity, and that can't be avoided. It essentially allows us to predict how things move under its influence, but it says nothing about why gravity exists or even how it works. It merely permits you to calculate things. Newton knew this clearly. He essentially said that it's down to God. In fact, he said that the most radiant blueprint of the sun, the planets, and the comets could continue under the area and course of a wise being. As such, he gave us the tools to sort out how the objects move around, but he said, "Don't ask me how or why. That's down to God." In the vast universe that envelopes us, there are mysteries waiting to be uncovered. Among these secrets are the astounding characteristics related to time and gravity, two fundamental bits of our world. Imagine a presence where time acts inquisitively, where it can dial back or speed up, and where the power that keeps us grounded may not be what it appears to be. This is the area of Albert Einstein's theory of relativity, where we could decipher time and gravity heading off in an unexpected direction. Albert Einstein, a name known to many, gave us another perspective on the universe with his theories of relativity. His work established the groundwork for how we could understand how time acts under various circumstances, especially when we travel at unimaginable speeds. Everything started during the 20th century when Einstein proposed two fundamental theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, changed how we sort out existence in essential terms. It tells us that the laws of physics stay the same for all non-accelerating observers, regardless of their movement. This theory introduces the concept of relativistic effects, including the prominent idea that time can stretch or slow down under specific circumstances. One of the most charming mental tests used to grasp time dilation is the light clock. Imagine being inside a spaceship moving at a fantastic speed close to the speed of light. Inside the spaceship, there's a light bar bouncing between two mirrors, perpendicular to the direction of movement. To an observer inside the spaceship, the light seems to go straight. However, to an external observer who's not moving with the spaceship, things appear different. They see the spaceship moving at high velocity and notice the light bar has to cover more distance to reach the mirrors. According to the laws of physics, the speed of light is constant for all observers, so the light bar seems to travel a longer diagonal path. Now here's where it gets interesting. The time it takes for the light bar to travel its path should be the same for both observers, the one inside the spaceship and the one outside. However, since the path is longer for the external observer, it seems like it would take more time for the light to complete its journey. This apparent time difference between the two observers is what Einstein referred to as time dilation. Time dilates for the observer moving relative to the fixed observer. So, in this case, time behaves unexpectedly. It depends on your movement. It's not just a concept. Tests have confirmed these relativistic effects. For instance, particles in particle accelerators like the Large Hadron Collider can reach speeds close to the speed of light. Scientists need to account for the effects of time dilation to make accurate predictions and measurements. The special theory of relativity opens up a reality where time is not constant but can be stretched or compressed depending on your movement. It challenges our usual instincts and forces us to acknowledge that the universe works in ways far beyond our normal experience. Einstein's special theory of relativity, presented in 1905, reshaped how we interpret the surface of the universe, particularly regarding time and motion. This theory, in its essence, reveals that the laws of physics apply consistently for all non-accelerating observers, regardless of their movement. To understand the special theory of relativity better, we need to break down its core concepts. One of the key ideas in the special theory of relativity is that the speed of light is the same for everyone, regardless of their movement. Whether you're stationary or moving at high velocity, light always seems to travel at the same constant speed, approximately 299,792,458 meters per second. This idea conflicts with our typical experience, where speeds often add up. It's as though the universe has a natural speed limit, and that speed is the speed of light. In special relativity, what we consider simultaneous events may not be simultaneous for everyone. If two events occur at different locations and you're moving relative to those events, what you perceive as happening simultaneously may not be simultaneous for someone else at a different vantage point. This seemingly impossible idea challenges our traditional concept of time. Time dilation is perhaps one of the most fascinating and significant implications of the theory. As mentioned before, time can slow down or stretch depending on your movement. The faster you move, the slower time seems to pass for you compared to a fixed observer. This effect becomes more pronounced as you approach the speed of light. Imagine two identical twins, one on Earth and the other traveling into space at a significant fraction of the speed of light. When the space-traveling twin returns, they will be younger than their Earth-bound sibling. This phenomenon, often referred to as the twin paradox, is a real consequence of time dilation. The reason for this surprising behavior lies in the invariance of the speed of light. As the space-traveling twin approaches high speeds, their clock seems normal to them, but to an observer on Earth, the space-traveling twin's clock seems to slow down because the twin is moving relative to Earth. Another consequence of special relativity is length contraction. As an object moves at high velocities, its length along the direction of motion appears shorter to a fixed observer. This effect is small at everyday speeds but becomes noticeable as an object approaches the speed of light. One of the most famous equations in physics, E=mc², is a direct result of special relativity. This equation states that energy and mass are interchangeable. It implies that mass can be converted into energy and vice versa. This principle is crucial for understanding the behavior of particles at high speeds and the energy released in processes like nuclear reactions. Special relativity is not just a theoretical concept. It has practical applications. For example, GPS systems rely on the precise timing of signals from satellites. However, because these satellites are moving relative to us, time widening impacts become an integral factor. On the off chance that the impacts of extraordinary relativity weren't represented in GPS estimations, our route frameworks would be fundamentally less exact. The unique speculation of relativity drives us to re-evaluate our instinctive thoughts of reality. It shows that the universe works in manners that oppose customary experience. Time is definitely not a flat-out idea but is relative, affected by movement. The steadiness of the speed of light and the connection among energy and mass are focal thoughts that have been affirmed by different trials. Currently, we should dig into the general speculation of relativity, one more wonderful thought set forward by Albert Einstein in 1915. This hypothesis brings us into the domain of gravity, uncovering a critical association between gravity and the genuine surface of the universe. At its core, the general theory of relativity challenges the conventional thought of gravity as a force that acts a good ways off between masses. Rather, it presents gravity because of the curve of spacetime. This thought is more clear than it could sound. To comprehend general relativity, we want to consider the universe as a four-layered substance, combining three components of space with one element of time. In this four-layered spacetime, enormous items like stars, planets, and even you, make the texture of spacetime twist around them. This ebb and flow is what we see as gravity. Imagine spacetime as a gigantic adaptable texture. A monstrous item like Earth makes a dimple in this texture. When you place a more modest item like a ball near Earth, it rolls toward the dimple. This is like the way an object falls, affected by gravity. It's not a baffling power. It's simply following the state of spacetime. General relativity gives a vigorous clarification for the movement of heavenly bodies in our nearby planet group. It precisely predicts the circles of planets, for example, the circular way pursued by Earth around the Sun. The old thought of gravity as an appealing force didn't completely represent these orbital developments, yet the concept of bended spacetime does. One of the most striking affirmations of general relativity came during the solar eclipse of 1919, when Sir Arthur Eddington led an endeavor to observe the bowing of starlight by the Sun's gravity. According to the hypothesis, the Sun's huge presence would twist the way of light from far-off stars, making them appear marginally moved from their standard positions. Eddington's observations matched Einstein's expectations, giving strong proof to the curve of spacetime. Another dazzling prediction of general relativity is the presence of black holes. These are regions of spacetime where gravity is so strong that nothing, not even light, can escape. Black holes emerge naturally from the states of general relativity, when an enormous star undergoes gravitational collapse, creating a singularity of infinite density surrounded by an event horizon, beyond which nothing can return. Recently, we've received direct proof of black holes through observations of gravitational waves, swells in the texture of spacetime caused by the acceleration of massive objects. When two black holes merge, they produce gravitational waves that travel through the universe. The detection of these waves by observatories like LIGO, Laser Interferometer Gravitational Wave Observatory, has affirmed the presence of black holes and offered further support for general relativity. One of the more mind-bending aspects of general relativity is the concept of time dilation near massive objects. Similarly, as time slows down when we move at high speeds, it also slows down in strong gravitational fields. This means that time passes more slowly for an observer close to a massive object compared to someone farther away. This effect, known as gravitational time dilation, has been observed and measured. For example, precise atomic clocks set at different elevations show that time runs slightly faster at higher altitudes, where the gravitational pull is weaker. The implications of general relativity are not limited to extreme galactic phenomena. They also play a crucial role in understanding the large-scale structure of the universe. The expansion of the universe, first observed by Edwin Hubble, is explained by the general theory of relativity. The theory describes how the texture of spacetime itself can expand and stretch, carrying galaxies along with it. The general theory of relativity has revolutionized our understanding of gravity and the universe. It reveals that gravity is not a mysterious force acting at a distance, but a result of the curvature of spacetime caused by massive objects. This rich idea has been confirmed by various observations and experiments, from the bending of starlight to the detection of gravitational waves. The concept of gravitational time dilation further emphasizes the interaction between time and gravity. Einstein's theories have changed our perspective on the universe, offering valuable insights into the nature of reality. While they may not provide all the answers, they have opened new avenues of exploration and inquiry. Einstein's hypotheses challenge us to re-examine the fundamental concepts of space, time, and the very nature of the universe. They suggest that our intuitive understanding of reality may be limited, and that the universe operates in ways that defy our everyday experience. The theories of relativity remind us that scientific knowledge is a journey of discovery, where each new finding leads to more questions and deeper understanding. Newton's theory of gravity laid the groundwork for understanding celestial mechanics, but it was Einstein's theories of relativity that transformed our grasp of gravity as an intrinsic property of spacetime. The special theory of relativity introduced the concept of time dilation and the constancy of the speed of light, challenging our ideas of time and simultaneity. The general theory of relativity advanced our understanding further by describing gravity as the curvature of spacetime caused by mass and energy. This idea not only explains gravitational phenomena, such as planetary orbits and the bending of light, but also predicted exotic phenomena like black holes and gravitational waves, which have since been observed. Einstein's theories continue to inspire and guide scientists in their quest to understand the universe at both the largest and smallest scales, uncovering a universe where existence is intertwined, and where gravity is a manifestation of the geometry of spacetime itself. As we continue to explore and test Einstein's theories, we are reminded that the universe is full of mysteries waiting to be unraveled. Each new discovery brings us closer to understanding the secrets of the universe and our place within it. How Newton could unravel gravity was adequate to permit us to fly from the Earth to the Moon. However, it kind of makes you laugh to imagine that you would have the choice to go the entire way to the Moon and back. This ultimately purposes something, I guess. All that in our universe seems to be brilliant. There are rules governing the whole universe, but certain secrets have stayed elusive despite various significant stretches of evaluation. Why does time travel in one direction? What is the nature of reality? Why does gravity exist? Why does time slow down when we travel at the speed of light? These questions have intrigued us for centuries. Consider how possible it is that I let you know that gravity really at stake. We need to go beyond Newton. The issue lies not so much in what he got right, but in what he neglected to resolve. There's a problem with Newton's theory of gravity. It basically allows us to predict how things move under its influence, but it says nothing about why gravity exists or even how it works. It merely provides tools for calculation. Newton was aware of this, of course. He basically said it was down to God. He posited that the most brilliant arrangement of the sun, planets, and comets could continue under the space and direction of an intelligent being. In that sense, he gave us the tools to understand motion, but advised us not to ask how or why. Those questions were beyond our reach and left to divine explanation. In the vast universe around us, secrets are waiting to be revealed. Among these mysteries are the curious eccentricities related to time and gravity, two essential aspects of our world. Imagine a world where time acts strangely, where it can slow down or speed up, and where the force that keeps us grounded may not be what it seems. This is the domain of Albert Einstein's theories of relativity, where our understanding of time and gravity takes a dramatic turn. Albert Einstein, a name known to many, changed our perspective on the universe with his theories of relativity. His work laid the foundation for a new understanding of how time behaves under different circumstances, especially when we travel at incredible speeds. It all began in the 20th century when Einstein proposed two fundamental theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, changed how we understood existence. Essentially, it states that the laws of physics remain the same for all non-accelerating observers, regardless of their motion. This theory introduces the concept of relativistic effects, including the remarkable idea that time can stretch or expand under certain circumstances. One of the most fascinating mental exercises used to explain time dilation is the light clock. Imagine yourself inside a spaceship moving at fantastic velocities, close to the speed of light. Inside the spaceship, there's a light beam bouncing between two mirrors perpendicular.